Going. So again, it says find the equation for the tangent to the curve at P, and they told us that the function was y equals 4 plus the cotangent of x minus 2 times the cosecant of x. So we need the tangent at P. All right, well, they gave us a coordinate. What I need is the slope, all right? So in part A, I need the slope of the tangent. All right, so that means I need the derivative. dy dx. Well, 4 differentiates down to 0, so I don't need to worry about that. Cotangent has a derivative of what? Negative cosecant squared x. All right, and this should be, I don't know why these are default colors, but whatever. So I need negative 2 times the cosecant of x, the derivative of that, but before we even get into the negative 2, what's the derivative of cosecant x? Negative cosecant x cotangent x. So take that negative 1 as the coefficient, multiply it by negative 2, and you get a positive 2 cosecant x cotangent x. All right, so in the left cabinet in the back, second shelf up from the bottom, I have a bunch of index cards there. Help yourself. When I run out of those, I have more. I have file cabinets filled with index cards. All right, so take them and make as many flashcards as you want. All right, you can do that now, you do it later. All right, these are some things that, I mean, you remember when we were deriving these using the limit definitions? It was not fun, right? I mean, okay, so it was fun in the learning and like learning new things process. It was not fun in the getting graded in math class aspect, right? If you were in an environment where it was just, we're gonna learn this just to learn it, and there was never any outside influences attached to it, it's like, oh, this is some pretty interesting stuff. But the minute you attach a grade to it, it's like, okay, now there's some pressure, right? So do we wanna do it with a limit definition? Of course not. Sometimes we have to, we don't have a choice. When you do have a choice though, you just want to know it, all right? And so we could just take a second here and jot all the trig ones down. The derivative with respect to x of sine x is equal to what? Just the cosine x. I'm going to go with the 3 most important ones, which again is not the SO, CA, and TOA. It's the SO, what would the next one be? The SO, secant, so, ha? Like, I don't even know. Like, secant x has a derivative of what? Secant x tangent x. The derivative of tangent is what? Exactly, secant squared x. Very good. Most impressive. I said that wrong, sorry. Impressive. Most impressive. So anyway, it's the sine, secant, and tangent. Those are the ones that you really, really absolutely want to know because their cofunctions have derivatives that are negative cofunctions. So d dx of cosine, just take the negative cofunction of the derivative of sine. So it would be negative sine of x. the derivative ddx of cosecant x, the negative cofunction of secant tangent. So negative cosecant x, cotangent x. Derivative of cotangent would be the negative cofunction of the derivative of tangent, which would be negative cosecant squared x. All right, so again, first three are incredibly important. Second three, not as important. It's nice if you know them. It would be great if you knew them because it just cuts down on reaction time, really. You know, it's like the difference between, you know, when you're loading up a web page. It'll load up eventually, or it could load up very quickly. Right? What's preferred? Like when you go to a website, you want it to just open up immediately. You don't like when it's taking forever to load up. You're like, oh, come on. Oh, let's get there. Let's go. You know, that would be if you didn't know these, and you had to discover them. But you know, you get there eventually. It's just it's a time crunch at that point. Right? So yeah, flashcards help, at least in the early goings. But down the line, this becomes second nature. You know, this is the sort of stuff that you'll take for granted. And so when we get to the point where we're taking antiderivatives, you know, working backwards, it'll be that much easier. So this course is really one semester of college calculus plus a few topics from a second semester. Antiderivatives we get into a little bit. And so that would be Calc 2. The Calc 2 material is a whole lot easier if you know all of your derivative rules. And because the people who struggle in Calc 2, they always say, well, Calc 2 is so much harder than Calc 1. And really, it's not. It's that you never knew Calc 1 to begin with. That's why you struggle in Calc 2, all right? And it's things like this. When I tell you, please know these things, it's for your own good, it's not like me preaching to you. I promise you that there is a payoff for you, a monetary payoff, all right? I mean, metaphorically in the form of points on a test, but also like, yeah, like money, like in life, when you get a good job because you've done well in math. You know, so yeah, there's a payoff in all aspects. Just by knowing these rules, these 6 rules, that's it. That's all you need to know. This in the unit circle.
Is there like a fun mathematical reason why the derivatives are negative cofunctions instead of cofunctions?
Yeah, it comes down to the graph, so. Yeah, we're actually going to, I'm trying to remember, I think it's before, I can't remember what I'm allowed to call it anymore. I used to call it the Christmas break, but I don't know what break, holiday break, is that what it's? Yeah, but aren't they all holiday breaks? You know, that's, so
winter break.
But that's the winter recess,
Oh.
yeah. So,
Is that winter recess though?
I don't know. I don't know anymore. So I'll call it the holiday break.
There you go.
All right, so I think it's before the holiday break that I have the activity for discovery of these relationships planned. So, yeah, because it's one of those things, like it's a good discovery thing, but yeah, it doesn't quite fit anywhere, so that's a good place to put it. All right, so we have those rules, which gives us this derivative, which allows us to find the slope at pi over 2. All right, so wasn't kidding about the unit circle. The derivative at pi over 2 I'm getting to the point in the year where all my classes are blending together. Have I used this notation yet?
Yes.
Oh, you have. Okay. That vertical line means such that. So the derivative such that the value is pi over 2. All right. In this case, because the derivative is in terms of x, it's implied that we're substituting in the pi over 2 for x. But we will work with cases where we're taking the derivative in terms of two variables, both x and y. In that case, you'd want to state explicitly where that pi over 2 is going. So I would say do I dx such that x equals pi over 2. If you want to play it safe, just write the x equals. I get lazy sometimes, though. All right, so as we know, because I've been repeating it over and over again, there's the calculator part and the non-calculator part. You have something like this with nice unit circle numbers, you can bet that it's going to be on a non-calculator part of the exam. So these are some things you want to know. All right. If it helps, convert it over into sines and cosines, which begs the question when we were deriving the derivative, which is a weird thing to say, but when we were discovering the derivative of tangent and secant, we had it as sine over cosine squared, and then we converted it into secant tangent. And I said at that point, like, this is the way textbooks write it, but it's probably better off to have it as sine over cosine squared. I honestly don't know why they converted over into secant tangent. They maybe, you know what, I know why. I just figured it out. In the early days of typewriters, they couldn't make fractions easily. Yeah, that's it. That's why they did it.
Of course.
Yeah. The technology that was available at the time made it easier for them to write it as a single line expression rather than as a fraction. I have no verification of that whatsoever, but it's got to be true. The theory that fits the facts is always true. That's why you can convict somebody in a court of law solely based on circumstantial evidence.
I thought you couldn't do that.
That's the joke. That would be the joke, yeah.
Okay. Wait, I don't know. That's okay. I wasn't catching on.
All right. I have to admit, I was more focused on making humor at that point than I was in doing math. So this could all be horribly wrong. So just double check me. It's good? Oh, wow. Pretty smart guy. All right. So when we put it like this, hopefully it's a little bit more obvious. Because the sine of pi over 2 is equal to what? 1. So negative 1 over 1 plus 2 over 1 times something over 1. What's the cosine of pi over 2? 0. All right, so this whole second part here zeroes out. Negative 1 plus 0 equals negative 1. All right, so after all of that, we've just gotten the slope. Our job was to come up with the equation for the tangent. So it seems like we have a ton of more work to do, but we really don't, because they gave us the point. They gave us the coordinate at the particular location. So what I would then do is write my point slope form. All right, y equals m times x minus x sub 1 plus y sub 1. We now know the m is negative 1. They told us that the x value was pi over 2. And the y value is what, 2? This cleans a little bit, but not in any kind of meaningful way. If I distribute it, I mean, I suppose I could drop the 1, but I mean, to rewrite the expression just to drop the 1 and make it just a negative symbol, that doesn't seem to make sense. If I were to actually distribute the whole thing out, I wouldn't even be able to combine the negative pi over 2 and the, well, actually it would become pi over 2 and the 2, like in any kind of meaningful way. So just leave it like this. And besides, this is the standard form. They call it the point slope form, but it's really what should be the standard form for the equation of a line. they actually call something else the standard form, and so they got the names all screwed up. But for consistency, this really should be our standard form. It lines up with the standard forms for every other type of function. Right? So if I needed to graph this, I have a point, I have the slope, I can just pop it in there. For any other type of function, I have a vertex and a slope, or a point of inflection and a slope, a lot of different things going on. All right, now the next part of it is focusing on the point at Q. All right, so we already have the slope for that. It's a horizontal line, and the slope is going to be equal to 0. All right. They gave me the point for x at Q, which is 1 comma something. I don't know the something. All right. But again, I do know the relation. I have y equals, again, 4 plus cotangent, 4 plus cotangent of x, minus 2 times the secant of x, cosecant of x. All right, so I just need to find the y value that goes along with that x value. All right, diagram notwithstanding, in the textbook it does line up with the 1, or at least it does seem to. So that's telling me I just need to figure out what y would be if x were equal to 1. So we're looking at y equals 4 plus cotangent of 1 minus 2 times cosecant of 1. All right, the x values are equal to 1. Now these are radian measures. You're taking the cotangent, sine, cosine, whatever, it doesn't matter, of things that are in radian form. We want things like pi over 2, pi over 3, things like that. We don't want 1s, 2s, just linear values of x. But we'll settle for it. It's perfectly fine. I do probably want to clean this up a little bit. Or at least try to. It may turn out that it's not really worth it. But it looks like I can get a common denominator. Just multiply top and bottom of this one by a sine of 1. And so I'd get the corresponding value of y to be equal to sine of 1 plus cosine of 1 minus 2 over the sine of 1. All right. Now, all of this is going to be for nothing, but this is how you would represent it. So let me show you why it's going to be for nothing. Or not for nothing, but the answer won't be as elaborate as what we did in the last question. Right?
Why don't you take the derivative in this part?
Oh, we already know the slope. It's a horizontal line. Yeah. So, again, the model. I lost my 4?
Yeah.
What? Thank you. All right, so since the slope is equal to 0, this whole part is canceling out. So whatever the y value is at x is going to be really our answer, quote-unquote answer. So it really didn't matter what form it was in. I could have left it as the original form or my new form, but basically it's telling me that y would be equal to this whole thing right here, or what it was in its previous form. All right, which is strictly numerical, because if I were to put that in my calculator, I would get some funky looking decimal value, and then that would be it. So then it begs the question, after you go through this entire progression, after the red step, was it necessary to do any of this stuff? Probably not, but you want to be prepared for it because you never know what's going to be the choice. you know, in a multiple choice question. So, but yeah, I mean, that's as funky in terms of numerical stuff as it gets. It's just a weird looking answer. All right, I'm just going. 25 next? Yeah?
Did not know what degree mode limits
All right, radians versus degrees. What happens to the derivatives of sine and cosine if x is measured in degrees instead of radians? To find out, take the following steps. With your grapher in degree mode, I love when they say that. Graph f of h. Oh, it's glitching now. F of h equals sine h over h. And estimate the limit as h approaches 0. Compare your estimate with pi over 180. Is there a reason to believe that the limit should be pi over 180? All right, so let's take a minute. Is that in radians, which is the world that we live in, and this is a pretty good reason why we live in this world, the limit as h approaches 0 of sine h over h is equal to 1, but in degrees, the limit as h approaches 0 of sine h over h, well, it appears to be approaching that point, which corresponds with the horizontal line, which we defined as pi over 180. So then the question becomes, well, what is the relationship between pi over 180 and 1? All right, so let's just go back to a little pre-calc here. We know that 360 degrees is the same as 2 pi radians, which means any variation on that would also be true. So we could say something like, if I want to divide, for example, by 2 pi, I would get 1 radian is equal to 180 over pi degrees. All right, so that is a relationship between those two units. All right, so if I wanted to actually do a conversion, I would work off of that. All right, so that's sort of what they're getting at here. Is there any reason to believe? Yes. Estimate cosine h minus 1 over h. All right, so they're basically asking us to do the same thing, but with the cosine rules. Cosine h minus 1 over h, so we'll use x's. I'll keep the same window. Looks like I can possibly go a little taller. Although we're going to have the asymptote there, so I don't necessarily need to go taller, but I'll do it just to satisfy the need to see a little bit more of the graph. I'll go like 0.05. All right, so it seems like it's verifying the asymptote. All right. So it says, now go back to the derivation of the formula for derivative of sine x in the text, well, text in our notes, and carry out the steps of derivation using degree mode limits. What formula do you obtain for the derivative? All right, so that's funny. Anyway. Where did they didn't even ask us to go, okay, whatever. So, derivation of sine. And we're going into degree mode limits, all right? So that's telling us that we're looking at, we're still having h approach the 0, sine x plus h minus the sine of x all over h. So all of this stuff. and I'll just carry through the process pretty quickly because we've done it before. So we're still approaching 0. Sine x cosine h plus cosine x sine h minus sine of x all over h. All right, so then the reorganization part would put these two guys together, and it would become sine x times cosine h minus 1 over h. And the other part becomes cosine x times the sine h over h. Still a limit as h approaches 0. All right, so now what this is telling us to do is use what we did in part A. I think it was part A, or an earlier part, and go with the degree mode limits. And that gives us sine h over h equal to pi over 180. So it's just the part that's annoying me is the fact that they never... Oh, okay. Yeah. So that was the thing that was I was missing. It says with your grapher in degree mode, estimate the limit as h approaches 0 of cosine h minus 1 over h. All right. So, and I never made a cosine. That's the other issue. Okay. There was like little language in there that was aggravating me, and I had no reason for it. Okay. So what that's telling me is that this part, no matter what mode you're in, this part is still going to be equal to 0, right, based on the graph in degree mode. So I'm still in degree mode, looking at my graph of cosine x minus 1 over x. We have every reason to believe that the limit of that would still be equal to 0, whether you're in radian mode or degree mode. All right, that was the part I was missing. So then what we get as a result here is that this would go to pi over 180 instead of 1. And so as a result, we would get pi over 180 times the cosine of x. All right, and that would be the derivative with respect to x of the sine function in degrees. All right, so I don't think anything else was really adding more to it than that. Because this says basically do the same thing again with cosine, but it's going to essentially give us the same idea. So when you take the derivative of a trig function in degree mode, there's also the multiplier of pi over 180 that needs to be accounted for. All right, so one component of this is that there's an extra piece that's just annoying, that you don't want to deal with, that you might potentially forget to deal with. The other part of it is, well, since most of the questions ask us to work in linear forms anyway, so feet, miles, stuff like that, rather than degrees, odds are this is not going to be overly necessary. Okay? If I need you to put an answer in degree form, if it's a trig-related problem, you do all the work in radian form to just convert your answer into degrees, rather than actually having a derivative that's totally in degrees already, right? So, but you never know what's going to come up on the exam. It has come up in the past, but like one time in the last half decade. So I think that's kind of like the rate at which this kind of problem comes up. So I wouldn't expect it, but you know, it is possible. So you just need that multiplier of pi over 180 every time you take the derivative if it's specifically in degree form. All right, but that's really what that question was getting after. Just, it took a while to get there. one day I had I still have every intention of sitting down and typing these questions or retyping them so that they're not as terrible, but time is a factor. Oh, yeah, 29. Oh, geez, I'm stealing my own thunder with this problem. But I wanted you to have an opportunity to play around with it first before because this is a fun one. If you figure it out, then you really feel pretty good about yourself. And so what I discovered over the last 20 or so years of teaching is that most of the time I was feeling really good about this and my students weren't because they didn't have an opportunity to explore the problem. But it's really cool. All right, so in order to really understand what it's talking about, you need to know what this means. And yesterday, and there's some inconsistencies with the way people do things, I would write this as that, all right, indicating that it's the 999th derivative of cosine. All right, so, I mean, if you happen to know that off the top of your head, congratulations. That being said, you really, I think, have a 1 in 4 chance of getting it right if you have a sense of this, so you should be okay. The idea would be to, well, okay, I don't know the 999th derivative definitely, but why don't we just start off with the first derivative? Which is what? Negative sine x. And the second derivative? Negative cosine of x, so I'm going to write it again as cosine x, negative cosine x. Move it up. Blue is next. Third derivative. Sine x. Very good. Fourth derivative. Cosine x? Yeah. So what happened? Back to where I started. It's a cycle. So it's a mod 4 cycle. All right. So you're looking at, if you're talking about multiples of 4 in your derivative, you're talking about the derivative being equal to cosine. One short of a multiple of 4, sine, 2 short, negative cosine, and so on. So, what's the nearest multiple of 4 to 999? 1,000. All right. So this would be equivalent to the 1,000th derivative. So 999 would be one short of that. All right. So. That's a cool one, right? When you get it on your own. I don't know how many you got of that, but when you get it on your own, you feel like a champ.
Is there a reason why it repeats like that the same way I does?
Say it again?
Is there a reason why it repeats like that the same way I does?
Yeah, because they actually both kind of follow the same rules. Yeah. So, did you learn the cosine plus I sine, the cis stuff in pre-calc? Oh yeah. The fastest route to complex numbers is through trigonometry.
Nice.
Yeah, there's the relationship there. And that's also, it's mainly because trigonometry is radical based. They're all square root radicals in disguise, so there's that natural relationship. I don't think the questions get quicker. Well, yeah, actually, I think 33 we already did something like that, and 35 I'm actually going to show you a different way to do it with L'Hopital's rule in like a week or so. So, yeah, I think we're good. All right, but if you need me to go over more tomorrow, I'm happy to do it.